is a problem from section 4.7. Oh, my pen's not tracking right still. This is applied optimization. Optimization is essentially max-min problems. So either we're going to try and do something min, like maximize the volume a container can hold, or maybe we know the volume the container needs to hold and we want to minimize the surface area. And we'll do one of each of those problems today and do some more tomorrow. So the problem we're going to look at is we have a sheet of cardboard or paper, and let's say it measures 8.5 inches by 11 inches, since that's standard paper in the US. And what we want to do is we want to turn this into an open top box. Come on, Ben. Here we go. Open top box. To do that, what we're going to do is we're going to make folds down each side. And the length that you choose to fold by here and here, we're just going to call that X. And when we fold it, that's going to go up, and we're going to get a box with no top, right? Okay. What we'll do in practice to make this happen is we'll make the fold, and then we'll make a cut along one side there. So then we'll have this flap here that we can fold and tape. So you're going to actually try to build this box right now.
Oh, that's what this graph paper is.
That's what this graph paper I handed out is for, yes. If anyone needs another piece of graph paper, let me know. All right.
Dude, should we try it? Just do it randomly? Do whatever you want?
Do that one.
Doesn't
matter what X is. No, you're just going to guess at what you think X should be to have a box that holds the most space inside of it. So this open top box, we are trying to maximize the volume. So you could have a very shallow box, not very tall, or you could have a relatively tall box.
Would it be the average of the two sides?
Well, that's a good question. Hypothesize. Make a decision. Fold, measure, cut, tape. Make yourself a box. Go for it.
Should both the x's be the same though?
It's the same value for X, because otherwise the short side won't match up with the tall side.
What's the
Long side.
box?
What's the volume of a box? Volume of a box is base times height. Where the base is the area of the base.
Which side's in inches?
So make your best guess. I'll make one too. And then after we'll measure and see who comes closest.
You already did this one before. You're cheating.
You've done this problem before?
No, you did it.
Me?
Yeah.
I know. I'm just going to make a fold and see what happens. There we go. That's my fold. What does it measure? So studio audience, I'll show a picture of what I'm doing in just a second. It's about 5.5. And I lost my pencil. This will work, maybe not. William, you're just in time for an experiment. We are building a box on a piece of paper. To build your box, you need to come up with a measurement. So you're going to fold up your sides, and that's going to make a box. You fold up your sides. So what you have to do is you have to decide what distance to fold up so that your box holds the most stuff.
What are we putting in our box?
Air.
Yeah. Okay.
Yeah.
'Cause if it's
I would say
30
water, but we probably have to wax it first.
It's 30 minutes then.
And we're not worried about sturdiness here. We're just worried about whose box holds the most air. Space. All right. So make your box, and then we'll do a calculus calculation and see what happens.
So this uses calculus. Is this anything like the problems in Math 95?
You may have done this in an algebra class too. You can do this without calculus, turns out, if you have a calculator.
Not very. Okay.
All right, there are lots of folding and see what happens here. All right, so let me switch to the camera view here. Where's my camera view? Right there, hello world. So here's my 8.5 by 11 piece of paper. And I decided to measure over 5.5 centimeters. Why 5.5 centimeters? I don't know. It's a nice number. And so I'm folding
Wait,
that
was
up
that
all
paper in,
around.
is that in inches or in
This is in, the paper's in inches.
Okay.
Yeah.
I was like,
I just
"Are you
prefer
supposed to
centimeters.
measure centimeters?"
So inches, measuring in inches makes me feel lonely because we're the only country in the world that does.
Okay, Mary.
All right, and then make a little snip or just fold carefully. All right, so now I am snipping along my edge. And then I'll tape it together and then we'll calculate. But I'm excited to see the diversity of boxes we have around the room.
What does everybody do the same one?
This becomes a yoga lesson where it's like.
Turn this into a yoga
This
lesson.
will represent your
Sure.
soul.
We could work this
These
into
are your
yoga.
chakras. These are your chakras. This is your personality analyzed.
All right, so
Yeah.
I am now
This is a BuzzFeed
taping
quiz.
my
What
box.
type of sub sandwich are you?
What type of what? Sub sandwich?
Have you ever taken those BuzzFeed
Yeah.
quizzes before?
Yes, I went to a meeting once where the icebreaker was, what kind of rock are you?
What kind of it?
It's kind of weird.
Yeah, here, one sec.
Okay, so here is my box.
It's short.
I have to calculate its size next.
Well, let's measure going.
All right, 5.5, that's how many inches? Almost 2.25. All right, so I'm gonna whip out a spreadsheet to make some calculations here. New sheet. So let's see, height. And we'll have length, width, and volume. My height, what did I say, it was 2.25 roughly? About 2.25, close enough. 2.25. Length is then 11 minus 2 of those. And my width should be 8.5 minus 2 of those. Oops, missing the equal sign. And the volume is the product of all of those. Oops. Oh, what did I do? I messed something up. Oh my. Oh,
How's it?
volume equals this times, oh, there we go, times that. No, times that. A times B times C. Okay.
Yes.
Thank you.
I like your box.
It's short and wide.
Oh, I forgot. I'm on the screen. All right. Anybody have a box that can show me? Oh my, check it out. Okay. So, let me see. I'm just going to show the studio audience out there. So, audience, we have a very shallow box. That's not very nice. We have a taller box than mine. So we have diversity going on. There you go. There you go. I'll show some more in just a minute. Let's see, Vitor, yours is done, right? Let's see. Ooh, yeah, that's in between all of those. So here's another different from mine. Different bases, right? Okay. So if you could, those of you who have finished, I need the height of your box. Let me switch back here.
4.5 centimeters.
What is going on here? Oh, it has all the measurements on it. Okay. So I'll show some more in just a second. Let me get some heights in here. Let's see, those are formulas. Okay. What was yours again, Vitor?
4.5.
4.5 inches tall.
Centimeters.
Oh, no, I need it in inches. Sorry. Yeah, because we started off with a standard US piece of paper. Sam, what's yours?
3 inches.
3 inches. We have a volume of about 60 cubic inches. What was yours, Rob?
2 5/16.
2 5/16. Oh, you're gonna get tricky on me. 2 5/16. Okay. Ooh, good. All right, Vitor, what do you got? Inches, roughly.
2 3/4.
3/4. No, I don't think so. You are 1 and almost 3/4.
1 3/4. There you go.
So let me see, that would be 4, 8, 11 sixteenths maybe.
Give some.
So 1, equals 1 and 11 sixteenths. Ooh, okay. Anyone else have a height in inches? Daphne, what do you got?
7/16.
7 sixteenths. Let's see, it'll treat that as a date unless I do equals. And what is yours, Ben?
2.5.
2.5 inches. Okay. All right. Whoa. So far, I've got the highest one. Oh my gosh. I just randomly folded the paper. Seriously, I did not plan that.
You know what it's supposed to look like, though.
You know, subconsciously I must. I haven't done this in years. I think I told you guys, I haven't taught Calculus 1 in a long time. So this is a problem that's not fresh in my head. All right. Everyone just about done taping? Let's take a look at some other boxes and then we'll do some calculus. So let's see, what do we got?
So much fun.
Harder than Ben, if I can display yours. All right, so we have a fine diversity of boxes. Check these guys out. Nice.
I feel like I made a tray.
That looks
We made a tray.
Or like,
I need.
It's another one.
Oh my
Yeah,
God.
you're on it. Awesomeness. Ooh, that is a sturdy box too. You had that folding and taping down. Look at that beauty. That is by far the best box yet.
Is that an orange thing? Oh, this is an
And
orange.
it is pretty darn close to the size of mine, which I think the volume showed.
Yeah.
I think you were the next closest, 71.6875. All right, so what we're going to do is we're going to try and calculate to see if I got lucky and did get the maximum volume for a box made with no top out of a piece of paper this size. Okay, calculus time. Back here.
Hey, can we make it a box?
All right, here we go. So, new piece of paper. And that pen's not tracking. I'm going to try this pen. There we go. Okay. So things we know that we started with a rectangle that was 8.5 by 11, and we had to make that fold exactly the same distance from every edge. And I said, let's just call that X. So all around here, I'm losing X on each side. So that means the 8.5 lost X on this side and it lost X on that side, okay? So as far as volume goes, volume is length times width times height. Length times width being the area of my base here. That's going to be my base. So let's say the length was 11, but I cut X off each side. So that means it's 11 minus 2X. The width was 8.5, but I cut 2 X's off each side. And the height, well, that's just the X when I fold it up. Okay, so that's the formula right there. We could, and we're trying to have a maximum volume, which means when this is graphed, it should look something like that, and we should be able to find that high point, right? So calculus can help us find that. What is that maximum volume? What X gets us there? Okay. So yeah, so we can either multiply this all this out, or we could use the product rule repeatedly. I think let's multiply it out. So some help with the calculator. What is 11 times 8.5?
93.5.
Okay, so we're going to get a 93.5, and then we're going to get minus 22x, and then a minus 17x, I think. And then a plus 4x squared. All of that eventually has to be times x. Switch colors here. So ultimately, I'm going to have a 4x cubed. I'm going to put that out front. And then 22 and 17 is 39. So minus 39x squared and plus 93.5x. Once I add like terms there and then distribute this x through. I think I got that right. What do you think, Rob? I do okay?
Yeah.
All right. So now we're ready to find the derivative of the volume with respect to that fold x. Okay, so we're letting that fold try and maximize our volume. And the derivative should help us locate the magic x value where that happens. So what do we get? 12x squared minus 78, sounds good. X plus 93.5. And this is a parabola, so when we set this equal to 0 and solve, we're going to get two different answers. Okay. This thing is a cubic, which means it wiggles somehow. So it's going to wiggle something like that. So there's going to be a maximum and a relative minimum on this curve. We want the max one, not the min one. We don't care about that one. Thinking about the domain of this situation, this is a cubic. Its domain is all real numbers. However, can I make any fold I want? No. So as far as x goes, for sure, I need to make a fold, which means x has to be greater than 0. However, if I fold the paper in half this way, I've got no box. I just have a piece of paper that's folded in half. So x can't be bigger than half of that short side. Okay. So half of 8.5 would be what, 4.25. So x also has to be less than 4.25. So x has got to be some number between 0 and 0.25. So a graph of this should show that right there is going to be 4.25. And so our answer's got to be somewhere in the middle. Will it be exactly in the middle, which would be 2 1/8? I don't know. Did anyone get 2 1/8? Let's go back to my spreadsheet here. Nobody quite got 2 1/8, but let's see if I type in 2 1/8, that would be 2.125, I think. Oh my, look at that. It's better than mine right there. Oh, maybe that is the answer. Okay, let's see.
This is
Peter Parker.
Wow, yeah, Peter Parker.
So well, is this a parabola? No, this is not a parabola. This is a hump in a cubic. It's this part right there. I'm kind of just zoomed in there. Okay. The derivative is a parabola. That's true for sure. So we want to figure out what two numbers make this 0. One of them is going to be the relative max. The other is going to be the relative min. So really, we're at the clutches of the quadratic formula here. So x is going to equal 78 plus or minus the square root of 78 squared minus 4 times 12 times 93.5. And I could care less about simplifying that. I'm just going to plug this into a calculator all over 2a. And it looks pretty likely we're going to want the -1, I think. Find out in a sec. So whipping out calculators, please. Let's see. Should I use a spreadsheet as a calculator? Oh, sure. So equals parentheses 78 with the minus the SQRT of 78 squared minus 4 times 12 times 93.5. Okay, that's inside the root. That's the numerator. Divide by 24. And I get 1.585.
Yes.
Okay, let's see what the other one is. Control X, Control V. Ooh, it's not what we do. Oh, I messed up. Control C, there we go. Control V. The other one, I just go in and swap out that with a plus. 4.9, can I make a fold of 4.9?
No.
No, okay, so this answer is out. All right, so let's just color that bad, no. All right, so then if I copy my volume formulas down, or actually I could just put this up here, right there. Oh, uh-oh,
That's not bueno.
that's not good. Somewhere I've got a mistake, because that is not the maximum volume, is it? All right, where's the error? Darn, I hate when that happens. Okay, this paper is, oh, the problem could be in my spreadsheet, actually, that I make an error in here. So the length, oh, what the heck? The length is not always 8. How did that happen?
Hey.
Let's see, this is the 8.5. This should be 11, oops, equals 11 minus 2 times whatever the fold is.
Math might not be so good anymore.
Oh yeah, look at that. All right, and this one doesn't really count. So mine was really 58.5, and Rob came close to it, but I didn't get the maximum.
I got worse.
2.125 is still better than mine, but the oh, look at that. Yeah, the 1.585-ish, it's got, so far, that's the highest one I see here, agreed? Okay, so let's look at the graph of it, because here I just have some scattered points, x versus volume. So just, I'm graphing, basically we're graphing the height versus the height versus the volume. So whip out your calculators. Highlight those. That's what I'm graphing. So Desmos to the rescue. All right, so volume of x equals 4x raised to the third minus, let's get 39 x raised to the second plus 93.5x is our function. And it should have a 0 over here at 4.25, which is half the width of the paper, so that's appropriate. And here I have this part, that's negative volumes, which we can't physically build with our paper. You know, maybe if we lived in the 4th dimension, but we don't, not today.
Is that true? If we lived in the 4th dimension, is that possible?
Yes, in the 4th dimension, I think that would be possible. So let's say I need to look higher. Let's go up to 70, and then I can see the peak up there. And Desmos says that peak should be at, or did I just click on a point? Oh, there we go. Oh, come back here. 1.585, which is roughly 3 decimal places to what we calculated. Where'd you go? 1.585. Yeah. And the corresponding volume should be about 66.148-ish. And Desmos says 66.148-ish. So graphing calculators enable people to find these values without using calculus. But where would we be without a graphing calculator? We would need calculus.
We would do derivatives.
Yeah, you need a derivative to figure out that point is there. Okay.
Can we make the optimal box?
So none of us made the optimal box. A couple of us got kind of close to it.
Can we
But-
do that? I want to make the optimum box.
You could do that later. We're going to do another cute problem, but I got to do some homework questions too.
Is there?
All right,
Does
so-
this paper? This next problem?
No.
You must.
Well, sort of. Okay. So I'm going to back away from optimization for a minute and see if there's any questions on section 4.6, limits at infinity. Maybe it's fetching data.
Uh-oh.
It's being really slow.
Yeah.
Servers are.
Yeah, I wonder if it's my open math that is having trouble today. Could be.
Maybe he's went on holiday.
Could be. They're ready for Thanksgiving at my open math.
Servers are.
Okay, maybe we're not going to go over homework questions right now. All right, let's do another question. If I have to, I'll extend the due date on that. Did anyone have homework questions? Okay, there were a couple. All right, so we'll check on that in a minute. Oh, there it goes.
Yeah.
All right. Which numbers? Anybody remember what they were stuck on? 10.
Yes.
Okay, find the equation of the slant asymptote of this rational function. So here, we can't use synthetic division to find it because the denominator is a quadratic. Synthetic division only works if the denominator is linear. So we have to use regular long division on this. And division is the only way to find a slant asymptote. So let's copy this sucker.
Long division.
All right, so
Long division, there we come.
It's like, how do you do that?
sorry, that pen is not, no, use that pen, it's still not working right. Let's try this one again. So that means when you do division, you got to fill in any missing terms. So this is missing the x term. So I'm going to rewrite that as 2x squared plus no x minus 5.
You do?
Yeah,
Fill in the-
otherwise you'll have some trouble when you come down here.
Do not do that.
2x cubed minus 10x squared plus 7x minus 22. It's most important on this side, but I usually fill it in there too. All right, so then I ask myself, what would I multiply by 2x squared to get 2x cubed?
X.
X. And then do that multiplication. So that gives me 2x cubed plus no x squareds minus 5x. And then subtract by adding the opposite. So then go through and change the signs. That's going to give me a minus 10x squared plus 12x. Oh, and bring down the minus 22. Then what would we multiply by 2x squared to get negative 10x squared?
-5.
We would multiply by negative 5. 5 times 2x squared is negative 10x squared plus 0x plus 25. And change the signs and add. So that gives me a 3. So we found that our, what's that?
Bring on the
Oh, 12x, right, thank you. 12x plus 3. Yep. So we found that this function right here, that's our f of x, can also be written as x minus 5 plus a remainder of 12x plus 3 over 2x squared minus 5. These are the same function. Now, if you consider what happens as x gets really big here, oops, it's supposed to be an x there.
Might be like negative 47 instead of.
Oh, yes, my goodness, I messed up my signs there. You are correct. Thank you, William. Yeah, yeah, I changed the signs and then I'm adding, so that's negative 22 plus negative 25. So that should be a negative 47 there. Good job. And then it's always a good idea to graph to check because it's easy to make a mistake like I just did. So let's whip out a quick graph of this. Desmos. So the original function is 2x raised to the third minus 10x squared plus 7x minus 22 all over 2x squared minus 5. I think I got that right. Right, and then our new one is x minus 5 plus a remainder of 12x 47 all over 2x squared minus 5, and they should sit right on top of each other, which they do. Okay, so got that right. So back here, so to confirm the asymptote, as x goes, that's supposed to be to an infinity there. What's going to happen is this fraction, oh, come on, pen. There we go. This fraction here, because there's a square in the bottom, it's going to go to 0, and this is going to dominate for large x. So f of x for large x values is going to be approximately equal to x minus 5. And so that right there is the slant asymptote. So we can double check that on the graph also. So back to Desmos. So I'm going to graph now y equals x minus 5. And notice this function is crossing if you zoom in. It goes up above its asymptote there. Go up to maybe 20. Let's try 15. Yeah, so you can see it goes up, goes over it, but then it's going to try and hug it from above. And it's just going to zoom in on it. But it's always going to be, it's not going to cross again, but it does cross once, yeah. And again, we saw before, a horizontal or slant asymptote can be crossed infinitely many times. It's possible. And every situation is a little different. My guess is this one only crosses once. It's not going to do it again. And there's another segment down here where it's hugging from the other side.
Wait, so in instances where it crosses its asymptote, does it actually like cross it like it equals a number at that point?
Yeah, so the asymptote isn't part of the graph, but it's controlling the behavior of the graph. Yeah, but they do intersect right over here somewhere.
Okay.
Yeah.
So like even
it's not a hole there.
With that sine one, when it crosses the asymptote, it always equals something at that point?
Correct.
Or, okay.
Yeah. All right. So again, the hard part was pulling out the long division. Other homework questions?
12.
Number 12? Thinking about it. Thinking about it. Maybe. Come on. You can do it. I think I can. If we have time, we're going to do another optimization problem where we design a can.
A what?
A can?
Like,
okay.
like a soup can?
A soup can, exactly.
Campbell soup can?
Yeah.
Does anyone know the dimensions?
Except we're going to revolutionize the soup can industry.
Because we're gonna make the most. I'm gonna sell this
All right.
research to.
Oh, there we go. Okay. So we want to evaluate this infinite limit as x goes to infinity. Excellent. So let's copy that into my screen.
Wait, is there actually work that you can do with this, or like? Because I I just kind of
Yeah, you
I
just,
kind of asked someone and they told me the answer.
so let's talk about it. So we know what the sine looks like, right? So let's just start off a little bit basic here. If you graph the sine of x, it's going to start at the origin and it's going to go up and down and up and down and up and down. Is it going to do anything else besides go up and down?
No.
No. So it's going up and down, and as it goes up and down, it's trapped between these two horizontal lines, which are y equals 1 and y equals -1. Now this function here, we've multiplied by -1, and all that does is flip the up and down stuff, okay? Multiplied by -3 here, that just changes the period, which is the distance, the length of a single chunk of wave. That's no big deal. And the +2 just shifts that origin point, okay? The +2 on the outside, however, that shifts the whole thing up, right? So my new sign is also gonna, so these are gonna move up too. So that's gonna go up 2, and this is gonna go up 2. So the new one is gonna go between y equals 3 and y equals 1. And it doesn't matter too much where it starts, because what are we considering here?
Where is as it goes?
Well, yeah, x is going to the right. So if this is later, this is some, for big x values, way away from the origin, what's this graph going to be doing? Well, it's just going to be jumping around between 3 and 1, isn't it? Okay. So a limit means it's heading to a specific number or heading in some direction. And it turns out as we keep, big x, there we go. We keep finding bigger and bigger x, and we look, what's going to happen? That same thing's going to be happen forever. So does this focus in on a specific number as we head out for bigger and bigger x? No, it does not. It just keeps bouncing back and forth between 3 and 1. So this limit does not exist because it keeps bouncing around.
If you're like sine x over x, would it approach 0?
Yeah, we looked at that last class. So if we were looking at sine x over x, the constraint there, if you think about normally the sine of x is stuck between 1 and -1, right? If I divide this entire thing by x, now I got to make an assumption here. I'm looking at x getting big, which means x is definitely greater than 0. So I don't have to worry about flipping my inequalities here, all right? That means the sine of x is trapped between -1 over x and 1 over x. And for big X, if you look at that, here's 1 over x heading down. -1 over x does the same thing, but on the other side. So this sine function right here is just oscillating in between these two forever and ever and ever and ever and ever. So since these two functions go to 0 as x goes to infinity, then the sine of x over x must also be squeezed to y equals 0 also. So that one does have a limit. Yeah, so it just kind of depends on what we're doing to the sine function to whether there's going to be a limit as x gets bigger. Okay. In the case of problem number 12 here, there is no limit because this function just keeps bouncing up and down between 3 and 1. All right, Kyler, what's up?
Could I, number 6?
Sure. Hey, that was snappy. All right, the limit as x goes to infinity. So this is a rational function. As x goes to infinity, rational functions, a variety of things can happen. They can go to infinity, they can go to -infinity, or they can go to some number. The rules we talked about a while ago are if the degree of the numerator and the degree of the denominator match, it's going to go to a specific number. And in this case, I think we have matching degree because that's a quadratic top and bottom. So use that one, sorry. So what I would do here is just multiply this stuff out. You don't have to, but I'm going to. So this would be the same as limit as x goes to infinity. And really all I care about are the big terms. So I'm going to have a negative x times a negative 4x, which is a negative 4x squared. And I'm going to have this other stuff, like what? A negative 6x and an 11x and a positive 66. And the bottom, what do we get? 2 times 9, there's going to be an 18x squared.
Negative 18x squared.
Oh, negative 18x squared, thank you. And then there'll be a minus 16x and a plus 27x and a 24. And I'm really not too worried about simplifying those two guys because the bottom line is the squares are going to dominate. If you're not sure of that, the trick I went over last time was divide by the highest power of x, which would be what here? It would be x squared. Yeah, so we divide each term by x squared. So if I do that, what's going to happen is negative, let's write limit again, x goes to infinity. Negative 4x squared over x squared, that's just going to be a negative 4. Minus 6x over x squared is going to be a minus 6 over x. Plus 11x over x squared is just going to be 11 over x. And then I'm going to have a plus 66 over x squared. Down below, it's going to be a negative 18. The x squareds cancel. Minus 16 over x, plus 27 over x, plus 24 over x squared. And as we let x get big, as we take this limit and we try to evaluate inside here, that goes to 0, right? That goes to 0. That goes to 0. Almost everything goes to 0 except for those constant terms that are left. So the limit is negative 4 over negative 18, which you could reduce down to 2/9. Which if you looked at it graphically, if you graphed this sucker and looked where it was going to, it would be going to about 0.22222. Harder?
The way I did it when I did this on homework,
Yeah.
I left it in its factored form,
Mm-hmm.
and I put an X under each of the parentheses. So
Yeah, that would work too. So you could just go in here and divide this by x, divide this by x, and so on. Yeah, that'll totally work too.
Okay.
Which if you're dividing this by x and that by x, then you're dividing by x squared top and bottom, right? So slight variation on what I did here. Another way to think about it, once you get used to this, you can kind of just look at it
Yeah,
and say, hey, I know these have the same degree. The squares are going to dominate for big X. So the limit has got to be negative 4 over negative 18. So you don't necessarily have to show all of this work, but this is one way to prove it, that the squares dominate. Okay? Tyler, does that help?
Yeah.
Okay. All right. So I think we have just enough time to set up the can problem. So here's our goal with the can problem. We've been hired by a major manufacturer who's tired of the US being in the imperial measurement system, and they want to design a can with a volume of 1,000 cubic centimeters, which happens to be 1 liter of the metric system.
chicken noodle soup.
Okay, so we have this 1 liter can we're trying to design. Now, they're environmentally conscious in addition to wanting to adopt the metric system. And so what they want to do is they want minimum volume of the can. Minimum volume. And it's got to be a cylinder.
Wait,
Oh my gosh.
this is not actually like important that I understand this, but why would that be environmentally conscious if they're going for minimum volume?
It's less.
I started minimum volume. I meant minimum surface area.
Yeah, I was
Oops,
like,
sorry about that.
Wouldn't you want it to carry more?
No, we're stuck. We have a fixed volume. Sorry, that was bizarre. Minimum surface area, right? They want to use as little metal as possible in making this can. Okay, so what's a can look like? Well, a can has a circular top, and it has this cylinder on the edge. And the cool thing about a cylinder is if you cut this and open it up, it's just a rectangle, right? The edge of a can, the side of a can is just a rectangle. So important features of this can is it's going to have a radius and it's going to have a height. So the volume is going to be the area of the base, which is pi r squared, times the height. The surface area of the can, however, has a circular surface here and a circular surface down here, and then it has this rectangular surface that makes the side of the can.
It's 2 pi r.
Yeah, so once you unwrap,
Double that.
once you cut and unwrap this cylinder, that top here is just the circumference of the circle on the top. And the circumference is 2 pi r, and there's the height. So that means the surface area of this can is equal to, I have 2 of those circles, so 2 pi r squareds, and then the side is going to be base times height, so that's 2 pi r times h. So that's the formula for the surface area. Surface area formula has a slight problem. There's too many variables. But we know it has to handle 1,000 milliliters. Sorry, I know I'm out of town, but just real quick here. So that's where we use this right here to minimize variables there. That pi r squared h has to equal 1,000. So then we could say h has to be 1,000 divided by pi r squared. And so we can use that information right there to substitute out that h right there. And then we only have an equation based on the radius. Then we can use calculus on it. That's what we're going to do next time. All right, we'll pick this up tomorrow. There is a similar homework problem to this, by the way. Feel free to play around. These problems take some time because there's a substantial amount of setup you got to do before you get to do the calculus. Then you get to do the calculus and check it. So it's definitely going to take a couple days to do this homework, get through this together.